Hi there, welcome to your lesson on the trapezoid rule for finding area under a curve. In the last lesson, you learned about the basics of integration and how integrating a function gives you the area under that function. Now we're going to look at a certain rule called the trapezoid rule, which is going to help us with this process. So this is a big idea here for you, for sure. Okay, big idea, definitely, big idea. And let's flash back to what integration is all about. We began with simple areas under curves. Let's say we have this purple, we can't really call that curve, but it's a purple function made up of two lines. Anyway, we want to find the area under that purple function. We can break the area into two geometric shapes that are easy to see, a triangle, and the area of a triangle is just half times base times height. So the area of that triangle is 3. And we can see this other shape here, which is a rectangle, but it's actually a square. And we can find the area of that, 3 times 3, and it is 9. So the total area under this function is 12. That's the most simple approach to finding areas under curves, but not all functions have angles and very obvious shapes like this. A lot of other shapes or functions are curved. When functions are curved, it's a little harder to find the area, right? But we can still try to use geometric shapes, for example, rectangles here. And here also rectangles. And we learned the idea that if you have rectangles under a curve, it can be used to approximate the area because it's basically approximately the right area, but there's always going to be some gaps and it's going to be imperfect. But if we increase the number of rectangles, or in other words, decrease the width of the rectangles, we can get more of them in there and the gaps are smaller. So it becomes a better approximation of the area until eventually you basically can take the number of rectangles to infinity. And if there's infinite rectangles, they will fit perfectly and we can find the area. And that act of making the number of rectangles infinite and summing their areas is what integration is all about. So here we learned the area under a function is given like this. It's the integral of the function from some starting point to some ending point, for example, a to b here. And that tells us put infinite rectangles there and combine them, take their sum to find the area. And this integral symbol actually means sum. All right, it means we're taking the sum. Okay, so let's say we knew that this function had this equation. Then that integral equation would look like this. The integral of that function from 5 to 9, let's say we also knew this point was 5 and this one was 9. So from 5 to 9, we're finding the area by taking this integral. Okay, that's where we've been. Let's take this a step forward now. Let's take a step forward in integration and finding areas. So let's look at this one to begin here first. We have the area bounded by a curve, and here's the function, the x-axis, and two vertical lines, x equals -1 and x equals a. We don't know what value this is. And we have an area. And it says the area is equal to 12. So in this case, we know the area, but we don't know one of the boundaries. So we're kind of going to have to work backwards in this one. Let's see how that's done. So here's our integral, first of all. To find the area, we're going to do the integral from a to b of the function. Okay, so here's the integral written in more detail. We have a beginning number -1. The other boundary, we don't know what it is, a, here's the function and that. So we can't really do this on our calculator, right? We can't find the area because we don't have that boundary. However, we don't need to find the area. We know the area. We know the area is 12. So we know that that integral produces a value of 12. So now we just have to find that other boundary. Of course, we can guess and check numbers. We can put different numbers in there, run the integral and see if we get 12. But there's another way to approach this on the calculator. So let's try it now. So grab your calculator. And let's begin by pressing math. There's a button on your calculator that says math. It's over here on the side here, on the left side if you look down. Press math and then scroll down that list until you get to B. On some calculators it's C, but it says solver or like equation solver. Okay, so math B solver. Okay, this is the screen you should now see. Now it allows you to put in two equations. So we're going to solve this equation because this is equal to this. So we're going to enter this integral as equation 1. So to do that, you're going to enter, again, math button, and then number 9 is FNINT, which is the integral function. So once you punch that in, over here you'll see this appear. I mean, it's not going to be that. It's going to have blanks here, but you'll see the integral ready for you to enter numbers into. Then you'll enter the numbers as we see them, -1 to x, some unknown value x, and then here's this. Okay. And then you're going to put 12 because that function equals 12 right here. And then you're going to press enter twice, enter, enter. and it will solve this for you. And I think it will give you a value of 2. So double check your work. You should get a value of 2 here. All right, that value of 2 then is our answer. It tells us that this must be 2. And if you went ahead and did backwards, ran an integral with -1 to 2 here, you would get the answer of 12. You'd see that. Okay, so you've learned a new skill in the calculator. Let's go on to something else now. Let's say we have this one. Well, actually, it's the same kind of problem. I want you to try that process again using math and then the solver. Try it for this one here. We're given that this integral produces this area. It says find the value of t and then describe what you see. Let's try. So the t value is 3. And the integral describes the area between this curve, the x-axis, and these two boundaries, which are x equals -1 and x equals 3. Make sure you know how to describe that when you see an integral. Okay, so I was interested in confirming that this works. So I'm going to run an integral on that. And on the calculator, this is what I got. I graphed the curve and ran the integral. Let me remind you how to do that. So here's the calculator. You're going to press y equals. Then you're going to enter your function. That's the function we have here on top. Okay, I entered the function and I can graph it. Let's see what the graph looks like. Okay, that graph looks like it's very close. I'm going to change the window on that one. So I'm going to go to zoom and then number 6 standard to get back to the standard graphing window. There's a standard graphing window. There's the graph. All right, now what we're going to do, while looking at the graph, we do second calc, and that allows us to find the integral, number 7. I'm going to run that integral, and it says lower limit. Well, I think this one we did from -1 to 3, right? So -1, enter, upper limit, 3, enter, and there it will find the area for us. That area is 5.33, and you can see here, that's what I have here, and that matches the area we have here. This gave that the area is 16 over 3. 16 divided by 3 is that number. Great, good to see that these things all work. Let's try the next thing here. So now we're going to jump ahead with our topic a little bit. We've talked about integrals. We've talked about areas under curves. Let's take it a step further. So here, there's an idea of a curve here. Here's some rectangles. Here's more rectangles. They're a pretty good approximation of the area under the curve. However, they're not perfect. My question to you is, what shape, and imagine in this diagram, what shape do you think would work even better than a rectangle for fitting under a curve? Okay, because a rectangle is always going to have these things above and below. What is a better shape we could use? Okay, the answer to that is this shape here. Notice we have, these are not rectangles. What shape are these? What shape are these things we've put under here? And notice they kind of go with the curve, right? Since they're not rectangles, they can go with the flow of the curve better. Well, those shapes are trapezoids. That's why we've been talking about trapezoids so much so far in this unit, because we're going to use something called the trapezoid rule to help us find those areas. Let's get into it. So let's say we begin with this curve. It gives us the equation of the curve, and we have the boundaries A and D, and we know what those boundaries are because we can see this is 4 and this is 8, so this must be 1, 2, 3, 4, 5, 6, 7. So this is 1 and this is 6. Okay, so we know the boundaries. We want to find the area. So of course we can begin just by running an integral, right? We know an integral gives us the area. So run this integral from 1 to 6. Here's our function, 12 over x dx. Put that in your calculator. What do you get? Okay, so we know the area under this curve is 21.5. That's the precise area. But now we're going to try and approach using trapezoids to find the area and see how close we can get to approximating the area. So here I've put one giant trapezoid in there. Okay, obviously it's not a very good representation of that area. There's this huge gap here. But anyway, one trapezoid looks like that. So how do we find the area of a trapezoid? Well, the area of a trapezoid uses this formula. Okay, and that formula comes from a basic trapezoid, right? We have one base, another base. The bases are always the two parallel sides, and then we have a height connecting the bases. And we find the area by adding the bases, multiplying by height, and then dividing by 2. Okay, so it's important to recognize where the bases of the trapezoid are, because this trapezoid here, we can see the bases are here. They're horizontal. But in this one, if you look for the parallel sides, it's this one and this one, right? So this is base 1, this is base 2. It doesn't matter which one you call which. And then the height then is connecting between the bases right here. So based on that, what is the area of that trapezoid? And do you think it's a good approximation of the actual area which we found here? So find the area of the trapezoid now. Okay, let's check our work. So there's the numbers we put in there. 12 for this base, 2 for this one, the height of 5, and our area is 35. Wow, that's quite different than 21.5 we got when we ran the integral. So again, the integral is the precise area. This one, using this one giant trapezoid, is a very bad approximation, but it's still better than if we had used one giant rectangle, right? Because one giant rectangle would have a lot of excess here. So trapezoid's better. It's not great. So what do we need to do? We need to do more trapezoids, just like we have here. So we took that same curve like we have here, but instead of one giant trapezoid, now we have 1, 2, 3, 4, 5 trapezoids. And notice now, these trapezoids are quite good at approximating the area. They're much better than if you had used rectangles again, right? Because rectangles would have a lot of excess either above or below the curve. These trapezoids are very good at following. Okay, so by creating more trapezoids, we can get a better approximation for the area. So let's get started on this. And to begin, we need to define what these points are, these corner points on each trapezoid here, because those corner points will then tell us how long our bases are, right? For example, if we know the coordinates of this point, we will know how long this base is. And if we know the coordinates of this point, we will know how long this base is, and so on. And specifically, we need the y values, because the y values are the height, right? So what is the coordinates of this point? Well, we know it occurs when x is 1, because this has been divided into 5 trapezoids. And we know that this is at 1, 2, 3, 4, 5, 6. So that means if we put an x value of 1 here, into the function, which is the original equation here, 12 over x, we should be able to get the y value. So I'm going to do that here. Here's the function, 12 over x. I put 1, replace x with 1, and I get an answer of 12. That means when x is 1, y is 12. So when x is 1, y is 12. That's that coordinate. And you might be thinking, well, that's pretty obvious. I can see on the graph that the y value is 12. But going through this process here is important in the moment when we create a general rule or equation for finding the areas of these trapezoids. Okay, so we have 112 here. How about this next point? What are the coordinates of that one? Okay, clearly the coordinates are, oh, that shouldn't say that. Let me change that. At this point, we have an x value of 2. And then again, we put the x value of 2 into the function, into this original equation of this curve. And when we put 2 in there, we have 12 over 2, which is 6. So that tells us that that coordinate is 2, 6. X value of 2, y value of 6. And again, we can confirm it here. So once we have those coordinates, it tells us how long the bases are. So in this first trapezoid, T1, this base has a length of 12, whereas this base has a length of 6. And then we know the height here is a 1 because each of these is a unit, 1 unit. So we can find the area of that trapezoid. So here's a big table which looks more complicated than it really is, but it's breaking down this process. Trapezoid 1, we can find the length of base 1 by putting 1 into the original function, which is what we did right here. And then we can find the length of base 2 by finding this y value, which we did also, so base 2 will be 6. We know the height is 1, and the height will be 1 for every trapezoid because each of them has a height of 1 here. And then what's the area? So what's the area of this first trapezoid, trapezoid 1? Okay, that area is 9. Check your work here. Notice we don't even have the 1 for the height here, because if we're multiplying by 1, we don't even need to show it. So there's that area. Okay, so what are the areas of the 4 other trapezoids, or the 4 remaining trapezoids? Tell me what they are now. And check your work here. We have areas of 5, 3.5, 2.7, and 2.2. So check your numbers carefully, and we basically now we can find the area under the curve, or we can approximate the area under the curve by adding all the areas of the trapezoids. So do that now. Okay, when you add up all the trapezoids, you get 22.4, and look how close that is to the actual area. We found the actual area by doing the integral originally, and now we have an area using trapezoids. It's very close, and we can see our trapezoids are a very close approximation. We can see a little bit extra here on this trapezoid, a little bit extra here. That's why we're a little bit higher than this number, but very, very good approximation. Okay, so let's take that step forward as well. Let's go back to how we found the height of these trapezoids. So question is, yeah, there's a height. Each of them has an equal height. How do we find that height? What was the process? Well, the process was to think about how we can split the full range here. So for example, if this is point A and this is point B, we know that we've taken that whole distance and we're splitting into 5 equal parts. So if we can find that distance and then divide by 5, we'll know how long each of these is, each of the heights. In our case, it was easy because they're all 1 unit. But again, let's say we didn't know exactly what the numbers are. Here's the process. To find the height, we do B minus A because when you subtract those, you'll get this full distance, and then you divide it by n, which means the number of trapezoids you're creating. So in our case, it was 6 minus 1. This is 6, this is 1, and then divide by 5, and that gives you 1. It tells you that every trapezoid will have a height of 1. Okay, so let's take that further now, and let's make a rule. So here is a curve. Here are 4 trapezoids used to approximate the area under that curve from here to here. Let's say that's A, let's say that's B. Again, to find the area, we can find an integral. Integral of whatever this function is from A to B. That would give us the precise area, but we're going to approximate it with a trapezoid rule. So let's say this is y0, or the initial y value, the second y1, y2, y3, y4, right? Those are the y values along the curve, which are the corners of these trapezoids. And in other words, they tell us the height, right? They tell us the height of each of these bases. The y value tells us the height. Okay, so now we know this height, we just talked about it, can be found by doing b minus a divided by 4 in this case. Okay, b minus a divided into 4 parts. So now let's write a rule. That's going to be trapezoid 1, and on and on. Okay, so the area of trapezoid 1, using the trapezoid area formula, is half times y0 plus y0, y1, which is this base plus this base, times the height. This is just the area of a trapezoid formula, right? The area of a trapezoid looks like this. Base 1 plus base 2 times the height divided by 2. So base 1 plus base 2 times the height divided by 2. Great. So the area of all the trapezoids then would look like this. Now this page is going to be filled with math. Don't be scared away by it. Let's just make sure we understand it. All right, so the full integral represents the full area. And notice we just have the trapezoid area written 4 times, once for each trapezoid. Here's the one that we had above here, area of trapezoid 1. Here's area of trapezoid 2. All that's changed is now we have y1 and y2, because in trapezoid 2, now this is one of the bases, and this is another of the bases. And look at in trapezoid 3. Now we have y2 and y3. These are the 2 bases. So there's a lot of similarities between each formula, but also that one thing that's different. So what we can do next is actually factor out the common thing. The common thing in all these formulas is half and the height, because the height is constant. So that half and the height has been factored out. And over here we just have all these pieces. The base 1 plus base 2 of the first one, the base 1 plus base 2 of the second one, and so on. Now notice what you can do with these. Here, when you add these up, I have y0, then I have y1, I have y1 again. I have y2, I have y2 again. So you actually have double of all those, except for the beginning and the end one. So this goes a step further to this. There's the factored part. Here's y0, and then there's 2 of each of these, because there's 2 y1s, 2 y2s, 2 y3s, and then only 1 y4. So beginning and end y values remain like this. All the other ones are doubled up. So this is called the trapezoid rule. It is used to find the area under a curve. So here's the rule given again. And we have y0, yn, because we don't know how many divisions we're doing. In the last one was 4, but we don't know how many trapezoids we're going to create. So that's n, and there's our rule. That rule can be used to find the area under a curve. Okay, so let's use this in this example here. Estimate the area under a curve over this interval 4 to 12. And we can see here we're given coordinates. And these are the coordinates of all the corners of the trapezoids. So 4, 5 is one corner, 6, 13, 8, 10, etc., etc. But you can see the interval x equals 4 to x equals 12, beginning and end. Okay, so how are we going to find the area under this curve using this rule? Let's take a look at the graph first. So these coordinates have been placed on the graph. You can see here 4, 5 is placed here. The next coordinate is 6, 13 right here. Then 8, 10, then 10, 3, and then 12, 4. So if there was a curve, it would go like that. We don't see the curve here, we just see the trapezoids. But these trapezoids are meant to represent the area under some curve that the curve passes through those points, right? Okay, so now we have those possible points for a curve. We have the 4 trapezoids. Let's use our rule here to figure it out. So area of trapezoid 1, for example, would just be 5 base 1 plus base 2, 13 times the height, and the height now is 2, and then times a half. That's 18. But of course, we're not finding area trapezoid by trapezoid. We're trying to apply this big rule here to save us the trouble of finding each trapezoid. Okay, again, we created this rule to give us a shortcut. So let's try to use the rule now to find the area under this curve, and not to do it trapezoid by trapezoid, but just try the rule. So see if you understand the rule and apply it to the numbers we have. See how you did, because it's always hard the first time. So let's check our numbers here. So here's the rule applied. Remember, the first part of the rule has the half and the b minus a over n, which was factored out, right? Because that is part of every trapezoid formula, but we can factor it out. Since it is part of everyone, we can just do it once. Okay, so there's that. Remember, b minus a over n is how we calculate the height. We take the beginning value and the ending value, we subtract them, and we divide by how many trapezoids. And that's what we're doing here. The first x value, sorry, the last x value is 12. The first x value is 4. So I do 12 minus 4, gives us a gap of 8, and then that's split into 4 parts. So this is like 8 divided by 4. It tells us that every trapezoid will have a height of 2. And then here is like the inside part of the formula. And remember, there we had the first y value and the last y value, and then all the other y values multiplied by 2 because they all came up twice, right? So first y value 5, last y value 4, and then 2 times all the other y values added up, 13, 10, 3. So by applying that, we can get our area under the curve. So try it. If you didn't calculate yet, try to calculate now, especially if you have to make some changes with the numbers. Let's see what you get. Okay, that gives us an area of 61. So I hope you're also able to work towards that same place. That would be the area of a curve that passes through those 5 points, approximated by these trapezoids. All right, great rule, great piece of integral calculus. Let's take that a little bit forward now. So here's that same thing we just calculated. And now I'm going to double check by using all the trapezoids, right? Because if we did one by one, hopefully this rule as a shortcut to doing all the trapezoid areas gives us the same answer, right? So here's all the trapezoids. If you did them one by one, you would have an area of 18 here, area of 23, 13, and 7. If you combine those numbers, well, unsurprisingly, we get 61. And that makes sense. And that just confirms that our rule works as a shortcut to finding all the trapezoid areas, right? It works. Good. Good news. Now let's take that a little bit further. Let's try another one, a little bit tougher. It says estimate the area under the graph of f of x equals e to the x over the interval 0, x is greater than 0 but less than 1. So we know our beginning x value is 0, our ending value is 1, and we don't know what this graph looks like, but we want to find the area under it using 5 trapezoids. So our first step is always to fill the table, right? If we have 5 trapezoids, that means we're breaking this distance into 5 parts. Okay, so we know you go from 0 to 1, and you need to have 1, 2, 3, 4 other intervals there. So what happens when you do, remember how we find the height? Because these are the height values, right? The differences in between each x value are like your heights of your trapezoids. So we take 1 minus 0, which is a distance of 1, and we break that into 5 parts. So if we break that into 5 parts, what's 1 divided by 5? It's 0.2. That means each of these has to go up by 0.2. So check it out. 0.2, 0.4, 0.6, 0.8, and 1. And you can see there's a gap of 0.2 between each of these. So imagine those again. Visually would be the heights of each of the trapezoids. Now, how do we find the y values? Now that we know x values, we can take them, put them into the equation, and get our y values. So what happens when you put 0 in here? What is anything to the 0 power? Well, that's 1. Anything to 0 power is 1. Okay, let's do the ending point. Let's put a 1 in here. What's e to the first power? Well, it's just e, right? Because e to the 1 is just e. E is, by the way, an irrational number, 2.7128, etc., etc. You should know that number. But anyway, what about these y values? And don't worry about getting decimal values for these. What would happen if you put 0.2 in for x here? What would you get? It would just be e to 0.2 power, and then e to 0.4, e to 0.6, e to 0.8. So now we have a full table. Once we have the table, we can use our formula, right? There's the trapezoid rule formula. Try it now. Okay, this one's a little tougher, right? Different kind of function, the strange exponential thing, but we apply the rule the same way. So to find the area under this curve, we are applying the trapezoid rule, and all the numbers work out to this. Check your numbers carefully, because now you'll need a calculator to calculate this. By the way, there is an E button on your calculator. Look for it on your calculator. Let me show you where it is. The E button is right here. It's above the division symbol. You press second and then that, and you get E. Okay, so now, just to confirm, you can also run that on your calculator, right? So let me show you how to do that. Okay, so I'm going to graph e to the x. There's e to the x. I'm going to graph that. Do I see something? Yep, it's taking time. There it is. Exponential growth curve. And I want the integral between 0 and 1. So really, I should change the window to be very small. Let me do that now. Notice how I adjusted the window here to show small x values because I only really need to see from 0 to 1. And then I'm going to graph that. So here's the graph slowly appearing. Then I'm going to run an integral on that between 0 and 1 and see if it matches the area we approximated using the trapezoids. So now I'm going to do second calc. Integral is number 7. I want an integral lower limit, negative, I want 0. Upper limit of 1, run the integral, there it is, and that area confirms. And look how close it is to that area there. That's amazing. Our approximation was close.